Okay, let's go over 3.3. Okay, so 3.3 is sketching rational functions. Okay, so a rational function is a function where f of x is equal to p of x over q of x, where p of x and q of x are polynomials. Okay, so it's basically one function over another function. We call that a rational function. Okay, so if we have f of x equals x minus 1 over x squared minus 4, okay, this is a rational function. Okay, whose graph looks like this. Okay, so that's what that graph looks like. Okay, these little dotted lines, they're called asymptotes. Okay, that's an asymptote. Okay, it's called a vertical asymptote. Okay, because it's a vertical line and it's a boundary, it's a barrier that the graph cannot cross. Okay, so instead of crossing, the graph has to bend as it approaches this barrier. Okay, now the vertical asymptotes are where, or they occur where the denominator q of x is equal to 0. Okay, so if I were to take the denominator here, f of x is equal to x minus 1 over x squared minus 4, and I were to set the denominator equal to 0, then I could add 4. I get x squared equals 4. Take the square root, I get x equals plus or minus 2. And so I get x equals 2 and x equals negative 2. And these are going to be vertical lines. And we say these are our vertical asymptotes. Are the lines x equals 2 and x equals negative 2. Okay, these values make the denominator 0, which make the whole function undefined. So the function is undefined where? Well, the function is undefined at these asymptotes. We can't have -2 and we can't have 2. We say that in the domain, x cannot equal -2 and x cannot equal 2. Okay? In the domain of this function, because it makes the denominator undefined. Okay. Okay, these values of 2 and -2 can be thought of as limits that approach two and -2, or I'd say 2 from the right, 2 from the left, -2 from the right, and -2 from the left. Okay, so again, looking at the original function, we have this type of deal going on. And then we've got this, and then we've got this. Right? And so what it's saying is that if we approach 2 here, okay, from the right, then where's the function going? Well, the function is going to positive infinity. Okay, as x approaches 2 from the right, so we say that the limit as x approaches 2 from the positive direction of f of x is equal to positive infinity. Why? Because the function is going toward infinity as x approaches positive 2. Okay, and we do a little 2 plus there. Okay, as x approaches. Now what happens when x approaches 2 from the other direction? What happens when we approach 2 from the other direction? Well, the limit as x approaches 2 from the left of f of x, that goes to negative infinity, right? That approaches negative infinity. Okay. What about the limit as x approaches -2 from the right? As this guy approaches -2 from the right, oh, that's going to positive infinity. And what about the limit as x approaches -2 from the left? Yep, as it approaches -2 from the left, yep, the y values are going down. And so they're going to negative infinity. Okay. Okay, what would happen if we talked about if the limit as x approaches infinity? What happens if x approaches infinity to this function? Okay, as the x values get bigger and bigger and bigger and bigger, ultimately what happens to the function? Well, let's see what we can do here. We have x minus 1 over x squared minus 4, right? Okay. So what I'm going to do is I'm going to, what am I going to do? Yeah, I'm going to divide both top and bottom by x, maybe? I want x squared or x. I want, yeah, let's do x let's do, yeah, let's divide both top and bottom by x. That'll be good. Okay, so we're going to say this is equal to the limit as x approaches infinity of x minus 1 over x, all over x squared minus 4 over x. Okay. So this becomes 1 minus 1 over x, all over x minus 4 over x. Okay. So now what happens when this thing goes to infinity? Well, 1 over infinity, that goes to 0. And this goes to 0. And that just leaves me with 1 over x. And 1 over x, well, that's going to go to 0. So the whole thing goes to 0 as I go to positive infinity. Now, what does this mean? That means that as the function gets bigger and bigger, this is a different color here. As the function gets bigger and bigger and bigger in the x values, what happens to the y values? Well, the y values are going to get smaller and smaller and smaller and smaller. So the limit goes to 0. And when a limit goes to infinity or negative infinity, we call this a horizontal asymptote. Okay, that's a horizontal asymptote. The limit going to infinity, or if the limit goes to negative infinity. What happens if, let's see what happens if the limit goes to negative infinity. Okay, well, very similar. Okay, we would say, aha, this is going to be 1 over negative infinity, which is still 0. So the whole thing still goes to 0. Okay, so we have a horizontal asymptote where? Well, the horizontal asymptote is at y equals 0. That's called a horizontal asymptote. Okay, it's a boundary that this thing is going to approach. As I go to negative infinity, this thing approaches 0 from the bottom. Okay, as I go to positive infinity, this thing approaches 0 from the top, but it still approaches 0. Okay, as I go off to positive infinity in the x values and negative infinity in the x values, the y values are getting closer and closer to 0. The y values here get closer and closer to 0. Okay, they keep getting smaller and smaller and smaller. Okay, so let's do a formal definition of this. As the limit as x approaches infinity of f of x equals 0, okay, so we say that there is a horizontal asymptote okay, at f of x equals 0. Okay. The limit as x approaches negative infinity of f of x is also equal to 0. Okay, as well. So we say there is only one horizontal asymptote okay, f of x equals 0 or y equals 0. Wait, I'm just going to say y equals 0 in this case. Now, you could get different horizontal asymptotes. It is possible. Okay. For example, if I had a function that looks like this, okay, I could get a horizontal asymptote of 1 as I go to positive infinity. The limit as x goes to positive infinity of f of x is equal to 1. The boundary that it keeps that it approaches here is 1, okay, as opposed to if I go negative infinity, then the limit as x approaches negative infinity of f of x is equal to negative 1. So it depends on, in this case, it depended on what, okay, where I was going, which direction I was heading was dependent upon, okay, the horizontal asymptote. Okay. Okay, let's do an example with this. Okay, number 1. Okay, find the vertical and horizontal asymptotes of the function f of x is equal to 3x minus 4 over x. Okay, so I have to ask myself to find the vertical asymptotes. Okay, vertical asymptotes occur when the denominator is equal to 0. Well, what's the denominator? It's x. So x is equal to 0 is the vertical asymptote. Okay, so that's the vertical asymptote. Okay, so now let's look at the horizontal asymptote. Where do the horizontal asymptotes occur? Okay, they occur when the limit as x goes to infinity of f of x. Okay, that's when they occur when x goes off to infinity. So what's this going to end up being? Well, this is going to be 3x minus 4 over x. I could put this, manipulate this. Okay, so let me rewrite this. This is the limit as x goes to infinity of 3x minus 4 over x, which is the limit as x goes to infinity of 3x over x minus 4 over x. So this is the limit as x goes to infinity of 3 minus 4 over x. And, well, what's anything divided by infinity? Well, it's 0. That goes to 0. So the limit here is equal to 3. Okay, so when x goes to positive infinity, this thing approaches 3. Okay, cool. Okay, and what happens when x goes to negative infinity? So the limit as x approaches negative infinity of f of x is equal to 3. Is equal to, I keep doing the same thing, is equal to the limit as x approaches negative infinity of 3x minus 4 over x. Okay, again, that is equal to the limit as x approaches negative infinity of 3 minus 4 over x. Okay, so now I'm going to put negative infinity in here for x, and 4 divided by negative infinity is 0. That still goes to 0, so 3 minus 0 in this case is still 3. So there is only one horizontal asymptote, at y equals 3. Okay, so we had a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 3. Okay, so let's graph this and see, why is this occurring? Why are these asymptotes occurring? What's going on with this thing? You know, what does this graph even look like? Okay, so let's go to Desmos, and I'm going to graph this thing. I'm going to say that, I'm going to say f of x okay, or y is equal to let's see, what do we want? 3x minus 4 over, oops. I guess it didn't like my handwriting. Let's try it again. 3x minus 4 over x. Nope. Let's not do that. 3, go away. Guess I have to use my finger instead of the pen. 3x minus 4. Oops. Minus 4. Not the whole thing. The whole thing. The whole thing needs to be over x. Okay, there we go. Okay, now I'm going to put in the asymptotes here. Okay, the first asymptote we said was y was x equals 0. So let's put that one in. X equals 0. X equals 0. Okay, I'm going to make this a dashed line. If I can. Maybe I can't. Okay, there we go. Can we do that? There we go. That looks better. Okay, done. And then I'm going to put in y equals 3 as well. Equals 3. Okay, and then I'm going to make that a dashed line. Okay, and done, and done. And let's see if this makes sense. Okay, does this make sense with the graph here? Okay, as x goes to infinity, what are we approaching? Well, we're approaching that green line, which is y equals 3. Okay. As x goes to negative infinity, what are we doing? We're also approaching that green line just from above. And so that's y equals 3. So yes, we have one asymptote here, okay, one horizontal asymptote. What about a vertical asymptote? Well, yeah, let's see. It approaches, as x approaches 0 from the left, it goes to positive infinity. As x approaches 0 from the right, it goes to negative infinity. Okay. So yes, those are vertical and horizontal asymptotes. Okay. Let's talk about the intercepts. Okay. Where's the intercept here? Well, there's only one intercept, and that's right there. Okay, at 1.333 and comma 0. The x-intercept is when y is 0, and the y-intercept is when x is 0. But x can't be 0 in this case, so there is no y-intercept. But there is one x-intercept, and it's right there. Okay, let's look at another problem, and we'll look for the intercepts on this one. Okay, okay, so the intercepts of rational functions okay, so we want the x-intercept. And to find the x-intercept, that's we let y equal 0. To find the y-intercept, we let x equal 0. Okay. So let's look at example 2 here. Okay, find all intercepts for, okay, f of x is equal to x cubed minus x squared minus 6x all over x squared minus 3x plus 2. Okay. So the first thing I want to do is, okay, well, let's find the x-intercepts. Well, if we want to find the x-intercepts, we got to let the function equal 0, let y equal 0. So to find the x-intercepts, okay, let f of x equal 0, okay, and solve for x. Okay, that'll give me my x-intercepts. Okay, so I'm going to take that f of x is equal to x cubed minus x squared minus 6x all over x squared minus 3x plus 2 is equal to 0. Okay, so what I'm going to do is I'm going to multiply both sides by the denominator. So it's basically just kind of like throwing the denominator in the fire. It kind of like that 0 there is going to burn it up. Okay, it's going to go x squared minus 3x plus 2 times x squared minus 3x plus 2. And then what happens to the denominator? It goes away. It kind of gets charred by this 0. That 0 just kind of, okay. Says, look, the denominator can't be 0. So there's no way to get that thing isn't even going to matter. When it comes to getting this thing equal to 0, I really only need the numerator to be equal to 0. So that thing goes away. Okay, so now we have to figure out what this guy is. I'm going to factor in order to figure out what the zeros are here. So I'm going to go x times x squared minus x minus 6 is equal to 0. Now I need to know what are two numbers that multiply to -6 but add to -1. Two numbers that multiply to -6, okay, but add to -1. Okay, well, maybe that's -3, right? Okay, if I were to add those, I would get -1. If I were to multiply them, I would get -6. So this is going to be x minus 3. X plus 2 is equal to 0. Now, this gives me 3 solutions. This tells me that x was equal to 0, that x was equal to 3, because if I plug a 3 in here, it gives me 0, and x was equal to -2. Okay, so that means I know that there are 3 x-intercepts. Ooh, that's a lot. There are 3 x-intercepts. Okay, 3 x-intercepts at where? Well, when x is equal to 0, y was 0. When x was equal to 3, y was 0. And when x is equal to -2, y was 0. Okay, so 3 x-intercepts. Oh, that's nice. Very cool. Okay, this one looks like an owl. Someone put ears on him. Okay, that's the origin. That's origin owl. Yeah. Okay. Who do you love? Okay. Who do you love? Okay, whatever. Okay, so now let's do the y-intercept. The y-intercept is a whole lot easier. You're like, good, because that was not fun. So the y-intercept is actually a whole lot easier because all you're going to do is plug in 0 every time you see x. So this is f of 0. Okay, if we go back to our original function, that means that it's 0. Look at our original function here. That's 0 cubed, okay, minus 0 squared, minus 6 times 0, all over. I mean, the whole thing is going to, the whole top is going to go to 0. So basically, we already know what the answer is. It's 0. 0 squared minus 3 times 0 plus 2 gives me 0 on the top and 2 on the bottom, which is 0. Boom. So there's only one y-intercept, and that was the origin. That was origin L there. Okay, so one y-intercept, the x and the y-intercept are, the same at the origin because they both go through 0, 0. So one y-intercept at 0, 0. Okay, a little owl there. Okay, he doesn't look like an owl. I got to make him look more like an owl. Ooh, ooh, ooh. There we go. Who do you love? Who do you love? Okay, there you go. There's that at the origin. Okay, so okay, if f of x is equal to p of x over q of x, then f of x is a function, right? It's a function. And therefore, there will always only be one y-intercept. Whereas there can be multiple x-intercepts. If it's a function, there will always intercept. Why? Because if it had more than one y-intercept, okay, it couldn't be a function. It wouldn't be. It would fail the vertical line test. Okay, so it has to be. It can have multiple x-intercepts, but it can only have one y-intercept. So there's the one y-intercept. Here's the three x-intercepts. So let's see what this bad boy looks like, and see if we got it right. Okay, so let's go back to Desmos. Get rid of you. Get rid of you. Get rid of you too. Okay, and let's plug this guy in. So y equals, oops, okay, y equals, okay, on the top, we've got x cubed minus x squared x squared minus 6x. Oh. Okay, I got issues here. How do I arrow over? There we go. X squared minus 6x. What the heck? Why does it keep doing this? Stop. Minus. There we go. Minus 6x. Okay, now on all of that over, highlight all of that and hit divided by. All of that needs to go over x squared, okay, minus 3x minus, or no, plus 2. Boom, okay. So, let's see what this looks like. So, what do we get here? We get 3 x-intercepts. We get an x-intercept at -2, 0. We get an x-intercept at 0, 0. And we get an x-intercept at 3, 0. We also get one y-intercept, which is at 0, 0. Okay. Okay, let's bring this all together. And let's do some graphing here. Okay. Let's do some graphing. Nice. Okay. Let's go back here. And get rid of this guy because it's not the graph that I had. Okay. The graph I had looked something like this, I think. With more scrunchier. Something like that. I don't know. Okay, 0, 0, negative 2, 0, and 3, 0. And yeah, 3, 0. Okay. So, guidelines for graphing. Okay, we'll call these graphing guidelines. So original. Okay, graphing guidelines. How do we graph with our guidelines? Okay, graphing guidelines. Okay, so A, we want to look for critical values. Okay. B, let's look for relative extrema. Okay, relative extrema. Critical values. How do we find our critical values? Well, our critical values are going to be when f prime of x is equal to 0, right? Okay, our relative extrema are going to be the values at those x values. Okay, C. Let's find the inflection points. Okay, and that's where f double prime of x is equal to 0. Okay, and using that, we will also want to figure out our concavity. Okay, is this thing, where is this thing concave up? Where is this thing concave down? Okay, this is first derivative test, second derivative test. Okay, so first derivative test, second derivative test. Okay, E, we want to look for the asymptotes. Okay, let's look at for the asymptotes. Asymptotes. Okay, that's the limit as x approaches infinity of f of x, limit as x approaches infinity, negative infinity of f of x. These will give me my horizontal asymptotes. Whereas if I have a denominator, okay, say that we have f of x equals p of x over q of x, then where q of x is equal to 0, okay, will give me my vertical asymptotes. And then f, the last thing that I want to get is the intercepts. Okay, so how do I find the x-intercepts? The x-intercepts let the original function equal to 0, and the y-intercept, we're going to let the x go to 0. Okay, so boom. So that's it. I mean, that's how we're going to graph this thing. Okay, we're going to do a, b, c, d, e, and f for the next function. Okay. Let's go through A, B, C, D, E, and F on the next guy. Okay, so number 3. Okay, sketch the graph of f of x is equal to 8 over x squared minus 4. Boom, okay. Okay, so where do we want to start? We want to start with our critical values. Okay, let's start with the critical values. We want to say, well, where is this thing going to be equal to 0 when I take the derivative? So A, critical values. Okay, so f prime of x, where is that thing equal to 0? Well, let's find out what f prime of x is. Let's use the quotient rule. Okay, the derivative of the top, that's 0, times the bottom, minus the derivative of the bottom, that's 2x, times the top. all over the bottom squared. Okay, x minus 4 squared. Okay, well, let's clean this thing up. This goes to 0. This is negative 16x all over x squared minus 4 squared. I want to set that equal to 0. Well, we can do the same thing that we used when we were finding the intercepts. Okay. And we can just multiply both sides by the denominator, and that kind of just goes in the fire and cancels out. Okay, if I multiply both sides by the denominator, okay, and so I get negative 16x equals 0. And so what's my only critical value? My only critical value here is 0. Okay, so that's my critical value. Okay, that's where I'm going to either have a relative max or a relative min. So I got to find out, well, which is which? Which is it? Is it a relative max or is it a relative min? Okay, well, let's look at our derivative around this value 0. Okay, so let's go to B. Okay, so x equals 0, that was my critical value. Let's look around 0 here to find our relative extrema. Is this going to be a max or a min? Well, we know that the derivative is 0 at 0, okay? But what about at -1 and at +1? Well, what was the derivative, right? What was the derivative function? The derivative function was equal to negative 16x over x squared minus 4 squared. That's what that guy was. Before I did that fancy multiplying of the denominator, that's what the derivative function was. So what happens if I plug in a -1? Okay, I really just care about the sign of this thing. Does everybody see that no matter what I plug in, the sign of the bottom is always going to be positive? Always going to be a positive sign. Because anything squared is positive. So what happens if I plug in a -1? Well, what's a negative times a negative? Oh, that's positive. Okay, what if I plug in a +1? What's a negative times a positive? Oh, that's negative. So this goes from positive slopes to negative slopes. Positive slopes to negative slopes means that there's a maximum here. Okay, so at x equals 0, we had a maximum value. A maximum value of what? Well, let's plug this in. Let's find out what's f of 0. By the way, this f of 0 here is going to be my y-intercept. So kind of kill two birds with one stone here. Okay, so plugging in f of 0, we get negative 16. No, that's the derivative. I want the original function. I get 8 over 0 squared minus 4, which is 8 over -4, which is -2. Okay, so at 0, -2, this is my max, which is also my y-intercept. So my y-intercept is my maximum. Oh, that's kind of cool. Okay. How do I know it's a y-intercept? Because it's 0 for x. How do I know it's the only y-intercept? Because there's always only one. Always only one y-intercept. Okay, so that's a relative max. Okay, so we've got a relative max there. Okay, now we want to find out the inflection point. Nice. Okay, let's see if we can find the inflection point. Okay, or is there even an inflection point? Well, what was the derivative? The derivative was f prime of x is negative 16x over x squared minus 4 squared. I want to take the second derivative and set it equal to 0 to get my inflection point. So let's do that. F double prime of x, again, another quotient rule. Derivative of the top, negative 16 times the bottom, x squared minus 4 squared. Minus the derivative of the bottom. Okay, this one's going to be a chain rule. This is going to be 2 times x squared minus 4 to the first power times 2x. That's the derivative of the bottom times the top, which is negative 16x. Oh, okay. Interesting, interesting. Okay, all over the bottom squared. So we're taking the bottom, x squared minus 4, and we're squaring the squared. We're squaring a squared, which means it's going to be to the 4th power. And then we want to do what? We want to set this guy equal to 0. Okay, we could probably simplify this first if we really wanted to. So we could say this is negative 16 times x squared minus 4 squared. Okay, this is going to be negative 2 times 2x times negative 16. So that's 32, 64, positive 64. Positive 64 x squared times x squared minus 4. Okay, so now I could factor on the top if I really wanted to. Actually, I could pull out an x squared minus 4. That would be helpful, because if I can pull out 1x squared minus 4, then I get x squared minus 4 times negative 16 times x squared, 1x squared minus 4 left over, plus 64x squared, all over x squared minus 4 to the 4th. So one of these is going to cancel with one of these, leaving me with a third. Okay, if I distribute the negative 16, okay, I get negative 16. Okay, negative 16 x squared plus 64. No, 16 times, yeah, 64. Plus 64. Plus 64 x squared all over x squared minus 4 cubed. Okay, so this is all getting the second derivative. So 64 minus 16, that's 48. So this is 48x squared plus 64 all over x squared minus x squared minus x squared minus 4 cubed. So let's see what we get here. Okay, and I want to set this thing equal to 0. Okay, so the first thing I want to do is multiply both sides by the denominator. X squared minus 4 cubed. That goes away. So now I get 48. I could factor out a 16 out of this. 16 times 3x squared plus 4 is equal to 0. Okay, divide by 16. And that goes in the fire. Okay, so we get 3x squared plus 4 is equal to 0. Okay, now let's subtract 4. 3x squared is equal to negative 4. Divide by 3. And we get x squared is equal to negative 4/3. Well, if I try to take the square root of this, I get an imaginary number. And that's not going to produce any inflection points. So no inflection points. Okay, there are no inflection. So there is no change in concavity. So this thing is always concave up or concave down. It's always one concavity. So what is the concavity? How do we know that this thing is concave down? How do we know that that thing's concave down? Any ideas? Okay, there's no inflection point, so the concavity never changes. So it's either got to be all concave down or all concave up. Well, what did we find? Didn't we find a maximum already? Didn't we find a maximum already? So where's the maximum occur? Well, at the top of the hill, right? So if there's only one maximum and this thing never changes concavity, then isn't this thing always going to be concave down? Right? So this thing is concave down. Okay. We'll say C max. Okay, so max is going to tell you, okay, that it's concave down. Okay, so C max. Okay, so let's kind of zoom out here. Okay, so what did we find? Maybe that's a little too far. Okay, what have we found so far? We found that there's a critical value at 0. Okay, got that. We found our max. We got that, which is also our y-intercept. Our max and our y-intercept. We got that. Okay, we found that there was no inflection point and it's always concave down. Okay. So let's go to E now. What was E? E was to find the asymptotes. Okay, the asymptote. So what was the function? F of x is equal to 8 over x squared minus 4. Okay. Okay, so asymptotes here are going to be, so the vertical asymptotes are going to occur when the denominator is 0. So vertical asymptotes when x squared minus 4 is equal to 0. Okay, and so I'm going to get x squared equals 4. And so x equals plus or minus 2. Oh, okay. So we know that there's a vertical asymptote at x equals negative 2 and x equals positive 2. So those are vertical asymptotes. Okay. What about horizontal asymptote? What happens as this thing goes to infinity? Well, f of x goes to infinity, the limit, so we'll say the limit as x goes to infinity of 8 over x squared minus 4, plug in a really big number for x, square that, and then divide that really big number by 8, or sorry, divide that into 8, I should say. Okay, divide that really big number into 8, and you're going to get a really small number. So this thing goes to 0. Okay, yep, exactly. The limit goes to 0 there. What if I plugged in negative infinity? Would it change anything? No, because we're squaring the x's. So if it will, even if it was a really big negative number, it would square and become a positive number. So it's also 0. Okay, also 0. Okay, so the horizontal asymptote is 0. Now, there is a problem with the concavity, and I want to address this. Okay, let's address this. Let's look at let's start putting the pieces together here. What are the things that I know? Well, I know that there's a vertical asymptote at x equals 2 and x equals negative 2. I know that there's a horizontal asymptote at y equals 0. Okay. I also know that there is a relative max at the point, what was it, negative 2 something, relative max at 0, negative 2, which is also the y-intercept. Okay. Okay, and so we know the y-intercept. Let's just get the x-intercept real quick. Okay. What would be the x-intercept? Okay. what happens if I plug in, can this thing ever equal 0? Can the original function ever equal 0, basically? X-intercept? Can I let the original function, x, 8 over x minus 4, equals 0? Is there any number I could plug in here that's going to get this to be equal to 0? No, if I multiply both sides of the equation by the denominator, I would get 8 equals 0, which does not make any sense. So there are no x-intercepts. That's kind of interesting. No x-intercepts here. Okay. Which kind of makes sense because there's a horizontal asymptote at 0. So it just means that this never crosses the x-axis. So we have, let me put this in different color. Okay, let's create our axes here. Okay, and then out at 2, I've got a horizontal asymptote. Okay, negative 2. At 2, I have another horizontal asymptote, and let's get a different color here. Let's get green. And y equals 0 is my horizontal asymptote. So I basically have 6 different areas. I don't like using that word, but it's basically 6 different fields that I could be in for my graph. I could be in this area 1, area 2, area 3, area 4, area 5, and area 6. Okay, those are the 6 places that my graph could live. Okay, because I have my 2 vertical asymptotes and my 1 horizontal asymptote. Okay, so I do know that I have what? I do know that I have a relative maximum at 0, negative 2. Okay, so I have a relative maximum at 0, negative 2. So I'm going to go down 2. Okay, so down 2. I'm going to put a point. 0, negative 2. That's my y-intercept, and it's also my relative max, which means that the graph more than likely, okay, looks like this. Okay, right there. However, when we talked about our concavity, we only talked about this one little piece of it. Okay, we didn't talk about what happens out here further away. Okay, what is the concavity doing, say at 3 or at negative 3? Is there more pieces of the graph? That's what I want to know. Okay, or is it just this one piece of the graph, or are there more pieces here? Okay, and yes, there are more pieces. Okay, of this graph. We know that that the second derivative was equal to, okay, was equal to 48 x squared plus 64 all over x squared minus 4 cubed. We got that as our second derivative when we simplify all of this. Got that as the second derivative. Okay, so let's plug in negative 3 and see what happens here. Is this concave up or concave down? Let's plug in 3 first. That'll be easier. Okay, f double prime of 3. Okay, so we get 48 times 3 squared. I don't really care, just care about the sign of this. 48 times 3 squared plus 64. Okay, all over 3. Okay, so this is going to be 3 squared, right? 3 squared minus 4 cubed. Okay, so the top is going to be positive. I know that's going to be positive. What's the bottom going to be? Isn't the bottom going to be 9 minus 4, which is 5, and then 5 cubed, that's 125, so that's positive. So what's a positive over positive? Positive. So that's actually concave up. We said that it was only concave down, but yeah, we were talking about the neighborhood here. It's only concave down there. But over here, it's concave up. Well, how can I have something that approaches an asymptote and is also concave up? Well, it would have to look like this. Okay. Nice, nice, nice. Okay, it approaches those asymptotes, but it's concave up. I couldn't have it be concave up down here. Why? Because I'd have another x, I'd have an x-intercept. And we already knew that there was no x-intercept. No x-intercept allowed. So if I had it down below and said, oh yeah, it goes up forever, approaches this asymptote, then it's going to go through the x-intercept, and I don't want that. It's going to go through the x-axis. I can't have that. Okay, so we know it's got to go like that. Okay, what about at negative? You know, I did -3. -3 is going to be exactly the same thing. I'll show you why, because we're going to get these squareds here. And what's -3 times -3? Isn't that still positive 9? This is going to be positive 9, and that's going to be positive 9. So it's going to be concave up in both spots. And so what are we going to get? We're going to get, okay, to look like that. Okay. Say no x-intercept. Like that. And there's our graph. Now let's graph this on Desmos to see if we came close. Okay, so let's see what happens. So let's go here. Okay, and this is just 8 over x squared minus 4, right? Yeah. Okay, so let's graph this. 8 divided by x squared minus 4. Okay, and let's see what happens here. Oh, look at that. Okay, that's nice. Okay, does it? Ooh, oops. Stay where you're at. Okay, what about the point 0, 2, 0, -2, sorry, point 0, -2. Okay, so let's label that. Boom, look at that. That's my relative maximum. Okay, no other relative mins or maxes except for that one. Okay, what about my vertical asymptote? That would have been an x equals 2 and x equals -2. X equals -2. Okay, boom, nice. Nicely done on the x-intercepts. And then on the horizontal vertical asymptote. What about the horizontal asymptote? Well, yeah, the horizontal asymptote is going to be y equals 0, which, okay, I gotta turn this stupid thing off. It wants to ink this thing. I gotta figure out how to turn it off. Like, just stop, drop, and stop it. There we go. Nice. Okay, perfect. Y equals, okay, I just want to bring that up all the time, but that's fine. Okay, y equals 0. Boom, look at that. Okay, so here's my graph, okay, with my intercepts, right? So this thing was concave down, okay, all the way along here it's concave down, and all the way up here it's concave up, and concave up, okay, and we have our one y-intercept, which is also a relative maximum, and no other relative extrema. Okay, so we put it all together, and we get a nice graph. Oh, yes, nice. Okay, I'm going to move on to 3.4 simply because I have time, and that will leave us only with 3.5 on Thursday, which is all application problems. Anyway, so it'll take a while to go through. Okay, so let's move on to 3.4. Okay. 3.4. So 3.4 is called absolute extrema. Okay, and it's actually pretty easy. If we know how to get a relative extrema, we know how to get an absolute extrema. Because all we have to do when we're dealing with absolute extremas, okay, is check the endpoints. That's all we have to do is check the endpoints. That's it. Okay, that's the only difference. Okay, to find an absolute means an absolute extrema or an absolute max or min is the maximum value or minimum value on a given interval. So we're just going to put check endpoints. Okay, check the freaking endpoints. Okay, given interval. Okay, check your endpoints. That's it. That's the only thing. That's the only difference here. Okay, so yeah, we gotta check our endpoints. Okay, so let's do that. Let's check our endpoints. Okay, we'll do 2 problems and then we'll be done for today. Okay, find the absolute extrema of f of x equals 4x minus x squared on the interval 0, 3. Okay, so what do we have to do? We have to find our relative extrema and the values at the endpoints and then compare all of them. And then that's going to tell us which one's the biggest and which one's the smallest. Okay. So, okay. So what do we need to do? Well, we need to find the derivative to get our critical values. We're going to do f prime of x is equal to 4 minus 2x, and I'm going to set that equal to 0. Okay, if I toss 2x to the other side, I get 4 equals 2x. Divide by 2, and I get x equals 2. That's my critical value. Okay, so I know that this thing's either a relative max or a relative min. Don't know which. I don't really care. I just know that it is one at this point. I don't really care which one it is. I just know that it is a relative max or relative min. Okay, so what I'm going to do is I'm going to evaluate the y value at this value, x equals 2. Don't care if it's a min or a max. I just want to know, is it a winner? Okay, is it going to be the absolute highest value or is it going to be the absolute lowest value? Okay, so I'll say this, absolute max or min, sorry, absolute maxes and mins only occur at relative maxes and mins or at the endpoints. Okay, they only occur at either relative maxes and mins or endpoints. Okay, so if I plug in f of 2, what do I get? Well, it was 4, well, the original function was 4 times x minus x squared. Okay, so this is going to be 8 minus 4, which is 4. Okay, nice. Okay. Okay, what about the endpoints? We got to check the endpoints. We don't know if this is the absolute highest value on this interval. We also don't know what the absolute lowest value is on this interval. So let's check the endpoints. Let's check 0 and 3. So what's f of 0? F of 0 is equal to 4 times 0 minus 0 squared, which is 0. So that's 0, 0. So I'm going to put these points here. 2, 4, 0, 0. Okay, 0, 0. Okay, what about f of 3? That's 4 times 3 minus 3 squared. That's going to be 12 minus 9. And that's 3. So this is 3 comma 3. Okay. So which value here was the biggest value? Which value was the biggest? In this column here, which value was the biggest? Not everybody at once. Okay. Yeah, it's the 4. Okay, it's the 4. It's, yeah, f of 2. It's the 4 here. Okay, so the absolute max, the absolute maximum value is 4. Okay, what's the absolute min? Okay, it's 0. Okay, it's 0. So this critical value did produce the absolute max, but one of the endpoints produced the absolute minimum. Okay, you're guaranteed on an interval to get an absolute max and an absolute min. Okay, why? Well, let's look at the graph of this thing. Okay, this goes through 0, 0. Okay, it also goes through 3, 3. It also goes through 2, 4. So 2, 4, and then 3, 3. Okay, and so it's actually a parabola. It's upside down parabola, and it stops here. Why does it stop there? Because we're only allowing, okay, the domain to go from 0 to 3. Okay, the domain goes from 0 to 3. That's the piece of the graph that I'm looking at. Does it continue afterward? Sure, it does. Okay, but am I allowed to go further? No, I'm not. So what was the absolute maximum value in this interval? Well, it was 4. What's the absolute minimum value? Well, it's 0. Easy stuff. Okay, last example. Okay, if an interval is not defined, then the interval is negative infinity to infinity. Okay, it's just saying, look, if you're in your domain is just it's the entire domain of f of x. Okay, I'll just say then the interval is the domain of f of x, because it's not, the domain of f of x isn't always negative infinity to infinity. Okay, so let's find the absolute value, or sorry, find the absolute extrema, not absolute value. Find the absolute extrema of the following function. Okay, f of x equals x to the 4th minus 8x squared. Okay, so this thing has no endpoints. Okay, so the entire domain of this polynomial, okay, is all real numbers. Okay, or negative infinity to infinity. So we're looking at everything. Is there a biggest value or is there a smallest value? Okay, for this function, that's what I want to know. Well, where's a good place to look? Well, a good place to look is at the endpoints. Oh, there are no endpoints, or at the relative max and min. So I've got to find all the relative max and mins, and then test those points and find out which one's the biggest, which one's the smallest. Okay, and then we're going to see. We have to analyze the graph a little bit too. Okay. So let's find the derivative here. And we get 4x cubed minus 16x is equal to 0. Okay, I'm going to factor out a 4x. We get x squared minus 4 equals 0. I'm going to factor the x squared minus 4. This is 4x times x minus 2 times x plus 2. So I'm actually going to get 3 critical values. I'm going to get x equals 0, x equals 2, and x equals negative 2. So these are all going to give me relative mins or maxes. Now, are they absolutes? We will see. We shall see. Okay, so what do we want to do? We want to plug these values into our original function. So f of x, f of 0 is equal to 0 to the 4th minus 8 times 0 squared, which is 0. So that's 0, 0. Okay, 0, 0. Okay, so that, we don't know if this is a relative min or a relative max. We really don't care. We just want to know what's the highest value, what's the lowest value. Okay, f of 2, let's try f of 2. This is 2 to the 4th minus 8 times 2 squared. 2 to the 4th is 16. Okay, minus, this is going to be 8 times 4, which is 32. So that's negative 16. Okay, so this is 2 negative 16. Okay, so that's kind of interesting. What about f of negative 2? Well, that's negative 2 to the 4th minus 8 times negative 2 squared. That's going to be the same thing, because if I take negative 2 to an even power, it's positive. If I take negative 2 to an even power, it's positive. Everything's positive here. So it didn't really matter if it was a negative or a positive. We're going to get the same number. So this is negative 2, negative 16. Okay, so these are my values, right? So I would say, oh yeah, the absolute maximum value here is 0, and the absolute minimum value is negative 16. Except I would be wrong. Okay, I would be wrong if I said this. Okay, only one of these statements is correct. Why? Because it has to do with the nature of the function that we're dealing with. Okay, let's look at the nature of the function that we're dealing with. The function that we're dealing with is this guy. Okay, x to the 4th minus 8x squared, f of x. Okay, so if I started, if x goes to infinity, okay, what happens to f of x? As x gets bigger and bigger and bigger and bigger and bigger, well, wouldn't f of x go to infinity as well? I mean, this is really, we're taking 8 times, once I get past 8, this thing here is always going to be smaller than this thing here, even after like 4. Once I get past the number 4, this thing is always smaller, and this thing's always larger, right? Okay, so really, okay, what does the graph look like? Well, the graph actually looks like this. Okay, it's a W. Okay, it's a W for Wumbo. Okay. And so what's the W? Okay, well, there's a minimum at negative 16, down here at negative 16. Okay, there's a relative maximum at 0, but then once I get past these intercepts, it just goes off to positive infinity forever. Once I get past this x-intercept, it also goes to positive infinity. So looking at the entire domain, there is no absolute max. There's no absolute maximum, but there is an absolute minimum at negative 16. So this thing was just a relative. It was not an absolute. Relative max, not absolute. Okay, these 2 points here were at the same height, which is negative 16. They're at the same value, and those are the minimum values. The minimum value was negative 16. So there's an absolute min at negative 16. There is no absolute max. Okay. Okay, we'll go over 3.5 on Thursday. Okay.